Hello guys, hope you all are doing well, and we are back with a new video, and today we are going to discuss something about spectral distribution of blackbody. As you can see on the screen, spectral distribution of blackbody radiation. We are just continuing our kinetic theory of gases ka concepts, and most probably in the coming lectures we'll be winding up with kinetic theory and we'll be quickly starting with some other topic. So yes, we are on to spectral distribution of blackbody radiation. So this was done by Lummer and Prinkshiam. So these two guys actually did this thing. So now what these two guys did, they took a perfectly black body. I think so perfectly black body is something we discussed in one of the previous videos, when we have two double walled hollow sphere, a conical projection, and a radiant energy incident, and it just keeps on going, multiple reflections in the Ferri's blackbody. So Prinkshiam and Lummer, what they did was they took such kind of a body, and they took this body at different temperatures, let's say T1, T2 and T3, and the radiations emitted by these bodies were studied, and the wavelength of light which was coming out of this body was studied. Now, so the emissive power of that black body and the wavelength was plotted. So if you can see, emissive power versus the wavelength was plotted, and this emissive power was plotted for multiple bodies. One body was at a temperature T1, the other was at T2, and the third was at T3, and the relation between them was T3 was greater than T2 is greater than T1. So T1 was the least temperature and T3 was the maximum temperature. So the wavelength which came out of that perfectly black body was not a single wavelength, it was a distribution of wavelengths. So the wavelength were starting from this point to this point. So the first body, which was at the least temperature, showed that for some wavelength it increases initially, it attains a maximum value, and then it further decreases. So this implies that for a certain wavelength, I'll call this as lambda max 1, the intensity of radiation was maximum. So if you see, this is the maximum intensity, maximum emissive power of a black body for this particular wavelength. So for this wavelength, the intensity was maximum. So what happens is this lambda max is for first graph. Now if the body was changed and if the body was made to radiate at higher temperature, then the distribution of the wavelength was something like this white curve. It initially increases, attains a maximum value, and then decreases further. This was happening for T2. And the maximum wavelength, maximum intensity, the graph is showing a maximum peak over here. So this was the maximum intensity or maximum emissive power for this particular wavelength. So lambda max 2 is this one. And then the black body was made to radiate at a higher temperature, let's say T3, and the wavelengths which was coming out of this black body was plotted, and we found out that the peak was again at somewhat different level. So initially it increases, then it goes maximum value, and then it decreases further. So the intensity was maximum at this point. So if you can see, this is the maximum point, this was the emissive power which was the maximum for this particular temperature. Now if you draw this line vertically down, then this is something what is called as lambda max 3, that is that wavelength for which the intensity is maximum. Same way for the second graph also, that wavelength, this is that wavelength at which the intensity is maximum. And for the first graph itself, that wavelength for which the intensity is maximum for T1. So what are the conclusions we can draw from this particular graph, which Lummer and Prinkshiam also made? The first and foremost is that the graph actually initially increases and then attains a maximum value and then further decreases. Second observation, what you can see is that the graph is not a linear curve. It's not a linear, it's not a straight line. It's attaining a maximum value and then decreasing. Third, what you can consider is, okay, it's a distribution. It's not a single wavelength. It's not a single wavelength which is coming out of that black body. It's a multiple wavelength, but yes, one wavelength has a maximum intensity. And if you see if you see this wavelength, actually when the temperature is increasing, the wavelength is shifting towards the left, and whenever things move left on the x-axis, it decreases. So the wavelength actually decreases if you increase the temperature. So if I wish to write here, then I can simply write like this, okay, lambda max 3 should be less than I'll just do it a different color, should be less than lambda max 2. Okay, so this is lambda max 2, this was lambda max 3, and I'll do it with a green, is less than lambda max 1. So you see, clearly there is a inverse relationship looking at this. So T3 is greater than T2, lambda max 3 is less than lambda max 2. T2 is greater than T1, but lambda max 2 is less than lambda max 1. Because as the temperature keeps increasing, the wavelength for which the intensity is maximum shifts towards the left. So just I have made into points. I'll just show you. Okay, so let's do one by one. So energy emitted by a black body doesn't belong to a single wavelength. So you do not have a single wavelength for a particular black body. You have multiple wavelengths. You have a distribution of, it's a distribution of wavelengths. It's not a single wavelength. So you have a range of wavelength, but there will be some wavelength which has an intensity maximum, which will have a maximum intensity. Then second is energy emitted increases initially, attains a maximum value and then decreases. That is pretty clearly visible from the graph, that energy increases initially, attains a maximum value and then further decreases. And the third observation is the peak of the graph shifts to the left, that is towards the smaller wavelengths with increase in temperature. So as you increase the temperature, the peak is actually shifting to the left. So if you can see in this graph, as the temperature increases, the peak shifts to the left. And last observation was the wavelength for which the intensity is maximum is a function of temperature. So if you see, this wavelength for which the intensity is actually going max is actually depending on the temperature. So as we keep on moving toward the higher temperatures, the wavelength is actually shifting. That means wavelength is a function of temperature. It's a function of temperature. Now in the coming videos we'll be seeing whether it's of course it's in indirect relationships. So lambda max is inversely proportional to temperature. Now in the coming video we'll be discussing about this law, which is called as the displacement law, where we also write it as Wien's displacement law. Okay, Wien's displacement law. But okay, that we will be discussing that in the coming videos. So I hope this small topic is clear, and in case if you haven't taken the notes, I'll just give it in just a single photo, so you can just screenshot this video, and also here also the diagram. So in case you haven't subscribed the channel, just go ahead and subscribe the channel, and hope to see you again in my coming videos. Thank you so much. Bye.